Sometimes the model is not the problem. The labels are. Cleanlab helps surface likely mislabeled examples before they poison training. You'll learn the shape of a workflow that audits your labeled rows to surface likely mistakes before training. I'm Professor Pi, teaching AI foundations with simple Python. Label noise is a silent killer in supervised learning. You can tune models forever and still hit a wall if your labels are wrong. Cleanlab label error detection is a practical way to find those bad labels before you waste compute on full training. People use it when datasets are hand-labeled, scraped from weak sources, or when classes are subtle and annotators disagree. The goal is simple. Point you to suspicious rows so you can fix or remove them, then retest your model honestly. Intuitively, Cleanlab trusts what a model confidently predicts across folds and flags cases where the given label disagrees with those confident probabilities. If a simple classifier is very sure a row belongs to class A, but the label says class B, that row is suspicious. Strengths are speed and clarity. Weaknesses include reliance on a reasonable baseline model and careful cross-validation settings. We will build a tiny reproducible example. It plants known label flips in a clean toy dataset, trains a baseline logistic classifier with out-of-fold probabilities, asks Cleanlab to spot issues, ranks them, and then retrains after dropping flagged rows to measure improvement. This shows whether the dataset or the model caused poor performance. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we generate a toy dataset where we exactly control which labels are wrong. This snippet constructs a structured toy dataset and marks the rows we knowingly corrupt. Ever wondered whether disappointing accuracy comes from your model or your labels? We answer that by stacking 3 clearly separated feature bands with numpy, so the classes should be easy to separate. Then, noise rows flips every 10th label, giving us a precise ground truth list of mislabeled positions for later diagnostics. Seeing corrupted rows equal the expected index list confirms exactly which examples will challenge the model later. With the noisy labels in place, we need to measure how much they hurt a simple classifier. This example gauges how badly the noisy labels distort a simple LogisticRegression cross-validation score. If the data is the villain, you'll see it right away in the drop from the ideal 1.00 accuracy. The function cross-val_predict gives us out-of-sample probabilities without ever fitting on the same pointed tests, so the object prob_cv mirrors what Cleanlab expects later. Comparing pred labels against y quantifies how the flipped rows drag the accuracy down, even though the features remain perfectly separable. Noisy CV accuracy exposes the exact performance tax we incur before any label cleaning. Now we feed the model's out-of-fold probabilities into Cleanlab to spot which rows the model distrusts. This code feeds those cross-validated probabilities into Cleanlab filter find label issues to spotlight rows that the model distrusts. The key decision here is whether the suspicious rows line up with the ones we know we flipped. The function compares each given label to the predicted probabilities in prob_cv and estimates which examples break confident learning assumptions. We capture its Boolean verdict in issue mask and turn it into suspect rows for an easy-to-read list. Because suspect rows matches our planted noise, we now have machine-checked evidence that labeling errors, not model bias, are the culprit. Marking issues by Boolean is useful, but in practice, you often want a ranked list so you know where to spend human effort first. This snippet escalates to Cleanlab classification, clean learning, so we can score each label rather than just mark it suspicious. The question now is, which bad labels deserve immediate triage when we cannot inspect every candidate? Clean Learning wraps our logistic regression clone, performs the recommended cross-validation internally, and returns a pandas data frame packed with label quality scores. By calling n smallest on that data frame, we rank the lowest confidence annotations without writing any extra ranking logic. Low quality rows pinpoints the top fixes to tackle first before investing compute in a full training cycle. Finally, we test whether removing the flagged rows actually helps the model, or if we just shrank the dataset without gain. This example retrains the logistic baseline after dropping the rows Cleanlab identified as label issues. The lingering doubt is whether removing those data points actually helps or just shrinks the dataset. We convert issues.df is label issue into a mask, so xclean and yclean keep only trusted training pairs. Running cross-val predict again on the filtered data lets us compare apples to apples with the earlier baseline. Clean CV accuracy jumping toward perfection confirms that the dataset, not the algorithm, was holding our model back. In a real project, you would map this pattern to your labeled pipeline. Run the same detection on each batch of new labels. Flag the top few percent for human review. If labels come from multiple sources, use the rank to prioritize which sources or annotators need retraining. Recap: we used a simple baseline and Cleanlab to find likely label errors, then showed how ranking helps you focus human review, and how removing flagged rows can recover model performance. Use this when labels are noisy, hand-annotated, or scraped, and you need to know whether the dataset, not the model, is the bottleneck. Just remember one caveat: the method depends on a reasonable baseline and correct cross-validation. If the baseline is poor, detection will suffer. Next step: scale this exact pipeline to a larger labeled set and add timing and accuracy checks so you can measure both quality gains and compute cost. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.